Welcome back to the course Introduction to Data Science. In this video, I talk about data transformations. And I will start with illustrating with an example why scaling of variables in your data set is sometimes important to do before you start your modeling phase. So assume that I have a data set with two variables, x1 and x2. And x1 is a variable, if I summarize it, it has mean 100 and standard deviation 50. Whereas x2 is a variable with a mean equal to 0.01 and a standard deviation of 0.02. So you see that the mean of x2 is much smaller than the mean of x1. And if I see variations in the x2 direction, they have, if I, for example, look in two standard deviations, it's 2 times 0.02. That is very small compared to the deviations you can expect in the x1 direction. So variations in the x2 directions are not noticeable in comparison with variations in the x1 direction. And especially if you are going to use machine learning methods involving distances between observations, scaling is very important. For example, in this particular situation with x1 and x2, the distances between x1 observations are much larger compared to the x2 direction. So if an observation is moving, then I mainly have to look in the x1 direction. That's where the biggest distance is realized. And I will illustrate this effect using a grouping algorithm. So I'm going to try to put observations in two groups, and you will see that this works if I scale the data, but if I do not scale the data, it does not give reasonable results. Assume my data set with x1 and x2 looks like this. And what I want is I want to put each observation in my data set in a cluster. Cluster 1 or cluster 2, cluster red or cluster green. So I'm going to force my algorithm to choose between two clusters. If I apply my clustering algorithm on this data set as it is here, then I find this result. Then clearly the algorithm says, well, you have two clusters like this. So you have, say, observations where x1 is small, roughly smaller than the mean, and the other cluster are the observations where x1 is larger than the mean for x1. These are my clusters. So it means that if you take, for example, this observation here, according to your clustering algorithm, it is closer to this observation than it is to, for example, this observation. Whereas if you look in the data, in the plots, then you would see, well, actually, I would prefer these observations are together. Whereas these observations, they can be in a different cluster because that seems to be a big distance. However, if you look at the scale of x1 and x2, then of course, if you go from this observation all the way to this observation, well, that's only a distance of roughly 0.4. Whereas in this direction, you are traveling, for example, roughly stating from here to here, it's a distance of 100. So because the scale of x1 is much larger than the scale of x2, I mostly classify in the x1 direction. What happens in the x2 direction, because that's so small compared to the x1 direction, is of no importance. To overcome the issue with the two clusters of the previous slide, I'm going to standardize my data first and then apply the clustering algorithm. What I mean with standardization, how you do that, we will talk about that later in the video. Assume that I apply the standardization. It means that I transform my data, so I start with x1, x2. I now transform it to a new data set, which here I indicate with x1.z and x2.z. So x1.z, x2.z is not my original data, that was x1, x2. It's new data that comes from my original data with a transformation. And what you see is now x1 and x2, they both have mean 0. And the deviations in the x1, in the horizontal direction, have the same magnitude now as the deviations in the x2 in the vertical direction. If I then apply my clustering algorithm, then my clustering algorithm correctly puts all these observations in one cluster and the other observations in the other cluster. So it's because, so we applied a clustering algorithm, it gave the wrong results. That was on the previous slide. But the problem was with us, we did not standardize the data. After we standardize the data, we again apply the same clustering algorithm and we find the correct results. So that's why clustering is very, no, not clustering. That is why scaling and data transformations are very important to apply on your data set. Let's have a look at the following two transformations. We start with the min-max scaling. In the min-max scaling, you locate the smallest value in your data set and the largest value, and then you take the relative position of x in between x-min and x-max. And that will give you a transformed data set. These are the x tilde values, and all the x tilde values are in 0, 1. Smallest value takes value 0. The largest value in your data set takes, after transformation, value 1. The problem here is, of course, that you have outliers that can distort your scaling. So in order to get rid of the effect of the outliers, you can also work with the z-scores. With the z-scores, you take your observation x, you subtract the mean, and you standardize using the standard deviation, and that gives you a transformed data, a transformed observation, which I denote by z here. In this case, different from the min-max scaling, the z-scores are not at 0, 1 anymore. Now you can have values which are larger than 1, for example. But I know that my mean of my transformed data set is 0, and my standard deviation of my transformed data set is equal to 1. Let me illustrate how you can do these transformations, the min-max scaling and the z-scores, using the data set that we had before with the car insurance. So I read my data here, and if I take the variable mileage, I'm going to transform that variable using the min-max scaling. So I will subtract the minimum, and then I take the maximum of mileage minus the minimum of mileage. If I have my transformed data, or my transformed mileage variable, I'm going to add that as a new variable to my data set. So I take my data set, which I have here, and then I add a new variable. That's why I use the $sign here. And then this is my new transformed mileage variable that I add to the data set. And here I'm going to create two histograms, one histogram for the original data, the variable mileage, and another histogram for the transformed variable mileage. If you run the code of the previous slide, you get this output. You get two nice histograms. The histogram of the non-transformed mileage variable, and then here the transformed mileage variable where I use the min-max scaling. What you can see is that if I look at the x-axis of the non-transformed data, you see that mileage takes very large values. It's mileage, people drive a lot. So you have a large mean with a lot of standard deviation. If I transform my mileage variable, you see that I put all the x values in 0, 1. So in the non-transformed data, you had large values for mileage. If I transform, always in between 0, 1. What you also see is that the shape of the histogram, it has like this skewed shape, that does not change after I transform the data. So I compress, in this case, the data, so I'm changing the x-axis, but the shape, the values on the y-axis, they're not changing. Let's then have a look at the z-score. So I'm going to create another variable in my data set. So I have now the variable mileage z, which is the mileage variable after I apply a data transformation. Now it are the z-scores. Here's a formula. So I take my original data, I subtract the mean, I divide by the standard deviation. And so in this case, the values for mileage after I transform the data are not in 0, 1, like we had with the min-max scaling. They now have mean 0, standard deviation 1. So I can test this. I can calculate the mean of my transformed data. I find something very small. This is 0, right? It's e to the power minus 17. For the standard deviation, R tells you it is exactly equal to 1. So that is what we expect from a variable after we transform it with the z-scores. On the previous slide, you saw the code to calculate the new transformed mileage variable with the z-scores. If you have the transformed mileage variable, you can again create a histogram like we did with the min-max scaling and compare this histogram of the transformed data with the histogram of the non-transformed data. So we have the non-transformed data here. That's the same histogram we had before. Now I transform with the z-scores. I look at the histogram. You find this result. And similar to the min-max scaling, the shape of the distribution does not change. So on the y-axis, we are not changing anything. It's on the x-axis that we are changing. But different from the min-max scaling, my x values when I transform my data are not in 0, 1. So you see that they take value between -2 and 3 and something. But the mean of my transformed data is 0 and the standard deviation is equal to 1, which means that I can find values larger than 1 and values smaller than 0, and that makes it different from the min-max scaling. In this video, we discussed two data transformations, the min-max scaling and the z-scores. If I apply the min-max scaling, then all the transformed data is in 0, 1. So that's convenient. I know exactly where my data is. It's in that small interval. If I apply the z-scores, I cannot use that property anymore. In that case, my mean is 0, my standard deviation is 1, but my transformed data can be negative, it can be larger than 1. But if I apply the rule of thumb that we discussed in the previous video, then being 2 standard deviations away from the mean means that my majority of the data is contained in the interval -2, 2. So I know something about where my data is located. What we also saw in the histograms is that both the min-max and the z-scores will not change the shape of the distribution and in particular will not change the skewness of the data. If you have a skewed distribution, after you apply the z-scores, it remains a skewed distribution. So we compressed the mileage variable in a smaller interval. So we changed the values on the horizontal axis, but we did not change the vertical axis. So we keep the shape of the distribution. If you want to change the shape of the distribution, then you need to use other type of transformations, which we will discuss later on.